Okay, so this gives you the theory you need in order to accomplish the homework. As I said, I have a half-hour recording. Think of it as a problem session where I explain some of the homework to you. But in the last 10 minutes of the class, I'll just give you an overview of what the homework is involved. So it's very much the systems that we've been discussing so far. I've done a little sketch here of, it's first of all in the homework, it's all MATLAB. Because I want you to see what's going on underneath, if you will, everything that's going on in OptiSystem. So it'll give you an appreciation of the validation. So this is all about validating theory, and for that you have to have somewhat more control, and it's also something you could do for your OptiSystem down basics. So anyway, we start MATLAB, but it's not a coding class, so I give you as much as I can of the code already. And in that code, if you look over it, what we see is we have a very idealized laser. So there's no phase noise, there's no RIN noise, it's just a perfect monochromatic source. One thing I do add to it that we'll be discussing next on Thursday is to give a pulse shape to the signal. So it's not just a necessarily a rectangular shape. We'll talk about other shapes which may be more desirable. And the external modulator we use, an ideal external modulator. I think there is a way of manipulating at least the extinction ratio, but I think the extinction ratio in the homework is very, very high, so there's not much effect due to a non-ideal external modulator. We have an ideal fiber. Again, it's just a zero dispersion. It simply introduces attenuation. So we have an optical filter. For the optical filter, the shape that we've selected is a super Gaussian filter. Again, the code is provided for you there, and we'll be specifying what the optical bandwidth is. We'll be varying that in the homework. The PIN diode is implemented as a square law detector with thermal noise and shot noise added. And of course, in your MATLAB code, we're adding the thermal noise and the shot noise, and we want to make sure that we're adding it in the correct way. So one of the things that we'll be validating is using the MATLAB code to run a Monte Carlo simulation of what the noise component is, and then you'll be plotting also a theoretical calculation of what the bit error rate is for these thermal and shot noise levels you've set, so that you can make sure that your code is properly run. And I'll tell you, the focus, I say I provide 90% of the code, and you're missing 10% of the code, and the 10% you're missing is about normalizing signal-to-noise ratio. And it's the largest source of confusion that I've seen with my students is how to correctly normalize the noise so that you can correctly interpret your results. So that's sort of the validation is focusing on that error, which I think happens quite frequently. So the electrical filter will filter this noise, and we're going to be also playing in the homework with different pulse shapes and different filter shapes on the electrical filter. So that's one of the things that we'll be varying in the main part of the homework set. Afterwards, we do a sampling at the symbol rate and then a threshold detection. As I mentioned, you'll be in the MATLAB code. They'll be calculating bit error rate with the optimal theoretical threshold and then comparing it with a numerically optimized threshold. That's one without ASE, and then we'll also be running the same experiments with ASE added. So you can see here there's optical amplification, there's a perfect gain, and then there's the ASE process. So there are the two aspects that will be examined. This is supposed to be you'll only be generating one wavelength. However, the equations we develop are also applicable to WDM systems because we are using an optical filter, so that optical filter could be used to isolate the channel, reduce the crosstalk, and in that case the equations that we have should be valid for even a WDM system. Again, this is all done in MATLAB. If you're interested in also comparing it with OptiSystem, that would be great. I don't require that for the homework. Anybody does it, I'd be happy to have a look at it. They should give the same results. Like I said, I just want to get under the hood a little more about the normalization to make sure it's being done correctly, but it's a valid point even with OptiSystem. So we're going to be assuming 50 gigahertz spacing on these WDM channels, which means essentially that we're setting the optical bandwidth of our filter. So our optical bandwidth of our filter is going to determine the level of ASE. So the objective of the homework is to validate the Monte Carlo simulations of bit rate against theoretical curves. So the first half, which I would like you to turn in before class on Thursday, is to generate the theoretical curves. So just take the subset of the code provided that deals